Our next topic is arch models. Arch models are used when one has non-stationarity in the variance. And again, what that means is that for our models, our time series model, we have these W sub t's, and they have a variance that's denoted by sigma squared W. However, if that variance is also dependent upon time, let's say we denote the variance now as sigma squared W t, then that says that we have non-stationarity in the variance. And arch models can help take that into account because it's going to actually model the variance directly as a function of time. Now, arch stands for autoregressive, conditionally heteroscedastic. We will also eventually, not in these set of notes, but another set of notes, look at its generalization, which are called Garch models, where the G stands for generalize. And lastly here, let me just mention that the person who developed these arch models won the Nobel Prize in Economics for this work back in 2003. So this may be the only time, or at least one of only a few times, that in a regular statistics course that most departments of statistics offer, this may be the only time where we get to actually talk about something that's won a Nobel Prize for the work. Okay, so when are these models useful? Well, sometimes when we have a time series plot, meaning that here's t, here's our x of t on the y-axis, we observe our time series over time, and all of a sudden we have a little bit of a variation increase. And here's another time. And so there's our data over time. And so in this particular case, we would have non-stationarity in the variance, but typically it's only for over a short period of time. Examples of where this happens are in various financial data, such as the corresponding to stock prices, bond prices, money exchange rates, and you can think about, well, why does that happen? Or maybe a better way to put this as, well, when have you actually seen this happen? I think if anybody who pays attention to, let's say, stock market indexes and stuff, we know that at times, maybe once a year, maybe once every few years, there's a lot of fluctuation in the stock market in terms of prices, the index values, and so on. And so what that's representing, that let's say that volatility, means that there's an increase in the variance of the prices and in the index values. So thus, this is the non-stationarity and the variance aspect that we talked about before in this class. And this is when these arch models can be helpful to take that into account. Now, in terms of what we've learned so far in a Riemann modeling framework, when we see non-stationarity in the variance, what do we typically do? Well, let's say that our time series is x of t. We will look for a transformation that maybe helps settle down that variability that we see, so that we have our variance of our series essentially as closer after the transformation. In terms of different parts of the series, the variance is closer to one another. So a very common way that one handles this is to use a natural log transformation of x of t. Now, even after that transformation, one's often not done, especially for financial time series. One has to deal with non-stationarity in the mean as well. So what one might do is do the first differences with respect to the log of the x of t. We'll call these first differences y sub t. Notice that now that y sub t would have a mean of 0. Then we can plot let's say, ACF and PACF of the y sub t, and it will look like the ACF and PACF are very similar to what we would expect if now we had white noise remaining. So in other words, then, a model for y sub t is an ARIMA 0, 1, 0, which I guess you could say is a little bit boring because there's no AR or moving average component at all to that model. But this often happens in financial time series. It actually corresponds to the efficient market hypothesis that you will often see discussed in finance, which simply basically says that excuse me, financial time series, like maybe like a stock market index, is essentially a random walk once you maybe account for non-stationarity in the mean, meaning that the index value, the current index value is simply equal to the most past index value, like time t minus 1, plus some random term, or WT. And so if we take a closer look at y sub t then, we can see that y sub t against the log of x sub t minus log of x sub t minus 1, or using properties of natural logarithms, we can take log of x sub t divided by x sub t minus 1. And if these are like stock prices, it's the log of the current value divided by the past value. Well, this is very, very close to what is often of interest in various financial time series, which is the return on an investment. And the way that we calculate the return on an investment is you take the current value minus the most recent past value divided by the past value. And so what this gives you is how much, in terms of a proportion, how much has the stock price, or whatever you're measuring, increase or decrease. So for example, if a stock price on the previous day was trading at $50 per share, and today it closed at $60 per share, well, what does that mean? That means then the return on the investment is 0.2 or 20%. A very good day for the stock. Now, obviously in ARIMA, 0, 1, 0 is kind of a boring model. But that often doesn't tell the whole story about what is involved with y sub t itself. Often, the distribution of y sub t has heavier tails than what you would expect if you had a normal distribution. And again, what that means is that you are having some y sub t values that are more extreme than what you would expect if you had a normal distribution. So for example, think of like a t distribution with degrees of freedom of, say, 2 or 5. Compare that to a standard normal distribution, and you can see that the t distribution has heavier tails. There's more probability out there. Also, what's very interesting is that these y sub t squares, so perhaps this is some measurement of the return of the particular stock. The squared terms are correlated, meaning that you have autocorrelation in the squared terms. Very, very interesting. Also, these changes in the y sub t tend to be clustered. So because of that, then one could say that there's maybe dependence in the variability or the volatility of these observed values. So let's take a look at two quick examples showing where this occurs. First, we're going to look at a classic data set. This is based upon the S&P 500 index from 1926 to 1991. And what we have here are the returns. So let's say the R sub t's. I'm going to end up calling them X sub t's. Sorry, perhaps I should have used R sub t in my my actual code, but I ended up calling them X sub t's. And so what we have here are the monthly S&P 500 index returns. So if for 1 month, well, let's say the first month that we have here, so for January 1926, the return was 0.0225. So that means if, let's say, you invested in an S&P 500 index mutual fund, you would have made, let's say, 2.25% in terms of your value would have increased by that much during January. And so we can put this into a TS class object by using the TS function as we've done before. Here's where my data is. I've read in the data using using read.table, put into an object called SP500, and the X component of this data frame is where my data is stored. I'm going to start in 1926, and the delta T argument tells our, okay, what kind of data do I have? Here I have monthly data, so that's why I have a 1/12 there. And so this is what the actual data looks like. Here again is January 1926. Okay, so let's do a plot of the data. And this is what we get. And so what we see in this plot, we see that variability often stays about the same for large chunks of this plot of the data over time. But then we see some other parts where we have lots of variability. So for example, this corresponds to now the 1929 crash of the stock market, and also then the corresponding Great Depression that occurred after that. Here, for example, we see some extra variability as well. This corresponds to what's often referred to as Black Monday in 1987, when we had a big downturn in the stock market. Here's maybe a little bit more variability right here in the mid-70s, which corresponds to various oil crises that were occurring in the world at the time. So what we see here is that we have short segments of time, typically, where there's a lot more volatility, which then equates to a lot more variability in these index values. Let's also take a look at a simulated time series that has this property as well. Don't worry about these particular settings that I'm putting up here right now, other than I have a sample size of 10,000. As we go along in this set of notes, you'll see what does alpha 0 mean, what does alpha 1 mean. But until then, don't worry about that. And so I simulated data from what's called an Arch2 model. And this is what we get. So again, similar to what we saw in the S&P 500 index plot, we have these short segments in time where it seems like we have a lot more variability in our time series than we would have at other points. This is a characteristic of a situation where an arch model would be appropriate. Now one could also do, let's say, the estimated ACF for my time series as well. And look at this. Notice I have such a large sample size. That's why you see the blue dashed line so close to the ACF line at 0. And we can see that in terms of the estimated ACF, we don't have any significant autocorrelations. We don't have any significant partial autocorrelations as well. So it looks like we have white noise essentially, but we don't exactly. We saw how that variability in that time series plot seems to be changing over time. But also take a look at this. If I were to do the estimated ACF for xt squared, notice you have what appears to be almost like a tailing off there. And if I look at the PACF plot, we look like, we have some significant values there, and depending upon how you interpret this, you could actually interpret it as tailing off. In the end, I will tell you, from what you'll learn about, this is actually cutting off, although it should be cutting off after lag 2, because I generated the data from an Arch2 model, and instead maybe it's lag 3, maybe even lag 4 there as well. So we have some significant partial autocorrelations. And so we're going to look at ways now that we can use what we see in those plots of the xt squares to help us understand this variability that we have that seems to be changing over time. So to begin here with introducing an arch model, we're going to look at an Arch1 model. And kind of a big picture here, why is understating variability important? Well, in finance especially, and this is where these kinds of time series, where these kinds of models tend to be most used. In finance, typically variability is associated with risk. So the more that the more that a particular stock price varies, the more risk there is associated with investing in that company. So the less amount of variability, then the less risk, because you are more certain about what's going to happen with that stock price. So variability equates to risk in investment. Investors expect to be compensated for taking on higher degrees of risk. So if I see a stock that's going up and down really a whole lot, well, if I'm going to put my money in it, I hope that in the end I'm going to be more likely to get a better average return in the end than if, let's say, I invested in a stock where there's a lot less variability and it's more constant through time, maybe this slow increase in price. If I'm risk adverse, I'd be okay with that kind of a situation. Maybe and also then in the end having less overall return. So it's like, the difference between putting your money in the bank, where savings or interest rates on savings accounts are low, versus putting your money in a stock market where perhaps you could make more money, but then because of that extra variability, you will maybe also lose your money in the end. Okay. So let's take a look at this model. Let's consider that we have our time series. We're going to call it y sub t. And we're going to look at a model that allows the variance to be dependent upon y sub t. So our model is as follows. And again, this is the most basic model. Y sub t is equal to sigma t times epsilon sub t, where the sigma t squared is written as a function of the past values of y sub t. Because it's an arch 1 model, there is one time period in the past that is in this representation. So alpha 0 here is going to be a parameter that we want to estimate. Alpha 1 is going to be a parameter that we want to estimate. Here's y sub t minus 1, that quantity squared. And epsilon sub t is an independent random variable with a mean 0, a variance of 1. This is an arch 1 model. Now notice, if I were to find the expected value of y sub t, I would get 0 from this because the random variable epsilon sub t has a variance of 0. Now, very often, and this corresponds to some stuff that I was talking about 5 minutes ago, y sub t is actually maybe a mean adjusted version of what we actually observe, let's say x sub t, so x sub t minus mu. Also, perhaps, y sub t could be the first differences for x sub t as well. Again, y sub t would have a mean of 0. And there's other transformations that you could look at as well. And so this is what our y sub t represents. Very often it's based upon some other time series x sub t that has been adjusted in some way to have a mean of 0. And we could relate this model then to what we would have for, let's say, an ARMA 00 model. So perhaps, let's say y sub t does have a mean of 0. We could set y sub t equal to what we would normally have as wt for our past ARIMA models. Wt, of course, is white noise, independent, mean 0, and variance sigma squared. Now, we could rewrite that model, though, like this, where we have sigma times w sub t, where now w sub t is independent with mean 0, variance 1. Now, the only thing that's different then with this model versus the model that we see up there is that I have a subscript t on sigma. This particular model up here allows for my variance to change as a function of the past. It allows for non-stationarity in the variance, essentially. And lastly, maybe this is overdoing it, we could even state the model like this, where we do, let's say, observe x of t. It has a particular mean, call it mu. There's my WT term. And we could write WT, let's say, as distributed independent mean 0 and then variance sigma squared sub t, where sigma squared sub t is equal to the alpha 0 plus alpha 1 times y sub t minus 1 squared. And all y sub t is simply the mean adjusted version of x of t. That's it. So we could represent models like this as well. Okay. Now, with our arch model, the variance changes. And so the H in arch comes from the word heteroscedastic. That's a term that's often used in statistics to represent differences in variability. So our variability is a function of time, essentially. Once we get into estimating the model, we will take epsilon sub t to have a normal distribution associated with it. As I said before, the alpha 0 and alpha 1 are actually parameters that we're going to want to estimate. They will have particular constraints on them in a very similar manner to how we've seen that with our Riemann models. Why do they have constraints? Well, for example, note that we need to have sigma squared sub t to be greater than 0. Now, another way to think about this model too, we can think of as white t as white noise with a variance depending on the pass. That's an arch model. Now, there will be times where we actually need to find an ARMA model for the original series x of t itself, because there happens to be autocorrelation associated with it, even after we take maybe first differences or what else we do, maybe some other transformation. X of t still may need to have an ARMA model. Then, basically, we work with the residuals from that model as our y sub t, and we use now a model for these residuals to account for perhaps this non-constant variance over time. Another way you could write your model as well is, just put in what that sigma t actually represents. And in terms of probability distributions here, if I were to condition on what y sub t minus 1 represents, well, y sub t actually has a normal distribution. So y sub t has a conditional normal distribution where we condition on y sub t minus 1. Mean is 0, there's your variance. Well, why? Well, just go back to how our model is originally presented here. This sigma squared t is the square root of that quantity right there. And so if I knew what y sub t minus 1 is, then I get a normal distribution for y sub t. Now, with this above representation, then, we can say, well, the variance of y sub t given y sub t minus 1, which is sigma squared t, is that alpha 0 plus alpha 1 times y sub t minus 1 squared. Also, the expected value of y sub t given y sub t minus 1 is equal to 0. Now, because of this, then, when we write out what a variance represents in terms of, now these are conditional variances, of course, we would have the expected value of y sub t squared given y sub t minus 1 minus the quantity squared of expected value of y sub t given y sub t minus 1. This is 0, so that means our variance is equal to the expectation of the squared y sub t. So another way then is to think of our expected value of y sub t squared given y sub t minus 1 as equal to what we were representing before as this linear combination of the alphas with the y sub t minus 1 squared. So this then gives you some information too about where other parts of this name comes from. So the autoregressive part comes from, well, I have a y sub t squared there, I have a y sub t minus 1 squared there, so that's where the AR part comes in. The C comes in because of the conditional part of how I was representing all that. Excuse me. Now, one could also represent our model as follows, just working with a little bit of algebra. This is how some people like to think of the model too. So what is y sub t squared? Well, here's y sub t squared again. How about I add and I subtract sigma squared t from there. Then I plug in, well, what does sigma t squared represent? Then, well, in my model, y sub t squared is sigma t epsilon t squared. And there's that extra variance that I had subtracted. Now what I could do is factor out a sigma t squared on the two terms on the right hand side. So I have sigma t squared there, epsilon t squared minus 1. How about just for convenience, I call this nu sub t, where this is a Greek letter nu. And again, you can think of this as like an AR1 model with this as playing the role of our WT that we have seen before. Just a little bit, so it's a little bit of a different air term. So again, this is where the AR1 part comes in for an Arch1 model. So, you know, conditional means, conditional variances are nice, but what happens if we look at the unconditional mean of y sub t, meaning just expected value of y sub t itself? Well, then what we can do is, to figure that out, is that we can go back to something that typically is taught in a mathematical statistics course. Not always, depending upon if you had like a 1 semester or 2 semester sequence for mathematical statistics. But we can use the following. Let's let a and b be two random variables. Then the expected value of a, and I'm going to emphasize that we're working with the distribution of a itself, excuse me, by putting the subscript there in a with the expected part, commonly done in statistics. I could rewrite then this expected value as the expected value with respect to the distribution for b of the expected value of a given b with respect to the conditional distribution of a given b. So that's how I could rewrite my expected value of a. In a more general way, let's say I want the expected value of some function of a with respect to the distribution for a. I could write this then as expected value with respect to the distribution of b of the expected value with respect to the distribution of a given b of g sub a given b. If you want to see an actual proof of that, this is typically found in many mathematical statistics textbooks. So applying that idea here, let's find the expected value of y sub t with respect to the distribution for y sub t. And what I'm going to do is y sub t is going to play the role of a, y sub t minus 1 is going to play the role of b in the previous expression there. So what I get then is in the middle here I have this conditional expected value, and we have already shown that to be 0. And so then the expected value of y sub t, expected value of 0 with respect to the distribution of y sub t minus 1, then of course is 0. So the unconditional mean is 0. What about the unconditional variance then? Well, there happens to be another. Oh, let me back up here a second. Here's my variance. I write it in terms of the second moment minus the first moment, and that should be squared. We just found that to be 0. And then using the expression that I had previously, we can now rewrite this so that in the middle here I have this conditional expectation where I'm looking for the expected value t squared. Okay. So this is a second moment. So I can rewrite it in terms of the variance plus the expected value squared. This expected value we know is 0. This variance is essentially what we're modeling. Alpha 0 plus alpha 1 times y sub t minus 1 squared. Now I have this expected value with respect to y sub t minus 1. I can move my expectation through the sum. And this is what I get here. And also, using properties that we've seen before with the causal model where we are not future dependent, then this expected value then can also be rewritten as the expected value of y sub t squared. Okay, so that's what the variance ends up being. And we can go further with this. Excuse me. So here's my variance. Well, let's write out what the expected value of y sub t squared would be. It's the variance of y sub t plus the expected value of that quantity squared. This is equal to 0, as we've already found. So I have a variance of y sub t here, a variance of y sub t there. Let's solve for the variance of y sub t, and what do we get? Alpha 0 divided by 1 minus alpha 1 for this particular model. Now we could also look at the kurtosis of a random variable. Again, this is a topic that's often taught in a mathematical statistics course, but not always. And what basically the kurtosis is it's based upon a fourth moment, where if I have some random variable a, it's equal to the expected value of a minus how far off or minus the expected value of a itself, that quantity to the fourth root. So that's why it's based upon a fourth moment. And we divide by then essentially what is the normal variance squared. So like a sigma to the fourth power. And with this fourth moment, basically it measures the peakedness or flatness of a probability distribution. The larger the kurtosis is, the more spread out the distribution is. So if I had, let's say, a normal distribution here, and let's say I look at this another normal distribution there, so this is, let's say, number 2, this is number 1. Number 1 is more spread out, so it would have a higher kurtosis. One could show that for a standard normal random variable, the kurtosis is 3. Okay. So let's look at now the fourth moment, excuse me, associated with the expected value of y sub t. One can show, don't worry about doing this, one could show that's equal to this quantity right here. This is the fourth, let's say, raw moment itself. Now to find the actual kurtosis, then, we would still need to divide by the variance squared, and we already know what the variance is, okay? Now, with this kurtosis, with this fourth, often people will say a raw moment, we can see that we have an issue here in the denominator, and so that means for us this alpha 1 has a particular constraint to it, because whenever I take the fourth, whenever I raise something to the fourth power, of course I need to have a positive value, so this expected value has to be positive, so we need this bottom here to be positive. In other words, we need 3 times alpha 1 squared less than 1. What this means is that now we have more information about these constraints on alpha 1. Alpha 1 can be between 0 and the square root of 1 over 3. Also, now if we look at the kurtosis, so if we take this value here, divided by the variance that we had above, squared, then the kurtosis ends up being this quantity, 3 times some function of these alphas. This function of the alphas is going to be greater than 1. So what that means then, this whole thing is going to be greater than 3, and so for a standard normal random variable, kurtosis is always 3, so these y sub t's then will be more spread out because the kurtosis is higher than what you would expect for a standard normal random variable. Let me make sure I stated that correctly. Y sub t will have fatter tails, or often referred to as heavier tails, than a standard normal random variable will have because of this result associated with the kurtosis. Now, because we have an AR1 structure for y sub t squared, that means a lot of the stuff that we've learned previously about AR1 models is going to still work out here if I were to find the, let's say, the ACF associated with the y sub t squares. So in other words, the autocorrelation for lag h for the y sub t squares is going to be alpha 1 raised to the h power. So what that means then for us when we're trying to figure out, well, various models, we can apply a lot of the stuff that we've learned previously with respect to autoregressive models. And you'll see this as we look at arch, let's say 2 models, arch 3 models, and so on. We can apply the same kinds of concepts in terms of looking at the ACF and also the PACF to figure out, well, what order should I have for my arch model? Okay. Now, how do we go about with parameter estimation? Well, we have this conditional result with respect to the normal distribution, so we can use that to set up a likelihood function. In the end, it's not actual maximum likelihood estimation that we're doing conditional maximum likelihood estimation because of this conditional property. I'm not going to go into further details about that. If you're interested, I have a resource here that gives you some of the details, but basically we're just applying likelihood methods with a conditional distribution. Now, one could also generalize an arch 1 model to, let's say, an arch M model, where M is the order or the number of what we think of as like AR components to our model. So we could have y sub t is equal to sigma t times epsilon sub t, where sigma t squared now is alpha 0 plus alpha 1 times y sub t minus 1 squared. Then we have a second term, and then we go all the way up to an mth term with this particular model. Epsilon sub t is distributed independent normal 0, 1. Again, the normal there is for our estimation purposes. The conditions on these parameters is that the alpha sub i's for I equal 1 to m, so excluding that one, all have to be greater than or equal to 0, and their sum ends up having to be less than 1. Okay, so these arch models are interesting, but they're not perfect either. Here are some weaknesses of these arch models. The model treats positive and negative returns in exactly the same manner. Well, why? Well, I have a squared there. Some people think that shouldn't happen, and there are extensions to these arch models that do allow it, but this is the way that we typically first present these kinds of arch models. Excuse me. And so that this is how it's first presented always in a time series class. The model is restrictive with respect to what values the alphas can take on, as we saw previously. And something that's really interesting too is that the model does not provide new insight to understanding the financial time series. Does not tell you, okay, in let's say 1 year, you will on average have a lot more money. Rather, what this is doing is focusing on a mechanism to describe the variance itself. And unfortunately, the model too can often overpredict the volatility because it responds slowly to isolated large shocks or large amounts of variability to the return series itself. So these are some weaknesses. It doesn't mean that we throw away these models. These are still good approaches. After all, this is what won the Nobel Prize. And as you might expect, as I kind of alluded to, we can generalize these models more to satisfy, to try to get around some of these weaknesses. But we need to start somewhere. And so this is where we're starting. Now, one generalization of this model is what's called a Garch model, where notice I say Garch order M and order R, similar to what we saw like with an ARMA model. Now, we'll have a whole set of notes on these Garch models, but I need to introduce them now because the functions that we're going to be using to eventually estimate these arch models are set up for Garch models. So again, the G stands for generalize. And this is what our model looks like, just like what we saw before. But now the sigma squared t, not only is it dependent upon these past values of y squared, now it's also dependent upon these past sigma squares as well. And we have parameters, the beta 1 through the beta r, that we will want to estimate. The epsilon sub t's is still distributed independent with mean 0, variance 1. For estimation purposes, we will start with a normal distribution there. So again, we'll talk about this kind of model more later. So this concludes now an introduction to what arch models are. Future sections of the notes, we'll look at how we can actually estimate these models and how we can work with R with them, and also how to choose the various orders for M with the arch models.